So far, I've not done anything particularly exciting. All I've done is I've just created a new project for us. Doesn't have any special dependencies. We're not going to really, this is going to be like a little more vanilla Scala. So we're not going to need any special dependencies, but I just created a different project here for organizational purposes. And I just created a little just shell here that right now is just going to say hello to us, just to make sure that my code's actually compiling and running. So let's go to project, functions, compile this, run this. Okay, so we are running. And as the name implies, the topic for today is partial functions. So I try to do a mix of kind of more, I guess, like applied or advanced things of like, here's like how you do a particular thing in ZIO, or here's a particular like library for doing Kafka or whatever. And we're definitely going to have more of that. But I also try to mix in some just basic Scala stuff of like, here's this concept, whether it's like partial functions, or I think we've done like pattern matching or path dependent types, or just different things like that. And I thought this would be an interesting one because I think partial functions are something that we, whether we realize it or not, we end up using at least a decent amount of the time, I think. But I think sometimes the like simplicity of it can make it a little bit less clear, like what's actually going on there and like what the trade-offs are. And in particular, partial functions have historically been used as a pretty big part of how HTTP libraries work in Scala. And that has some benefits, but also some cost to it. And there's some changes coming down the pipe for ZIO HTTP that's actually going to move away from this. So this isn't going to be like ZIO HTTP specific, but we'll kind of allude to that and kind of maybe lay the groundwork. So when you see that you understand a little bit more of the motivation and how we, and kind of where that's going. And yeah, how's the partial function HTTP routes matching? Yeah, that's kind of the perfect example. So let's see, I wonder if I think I have do I have a ZIO HTTP example here? I'm not sure, let me just make sure I download the latest. I'm not sure we have one here, but yeah, we can kind of sketch it out that like even in ZIO itself, like you would have something where you would be like http.collect ZIO, and then you would do something like this, and this is basically how you would define a root. I don't think it's quite, it's that. But basically this is saying, hey, if you get something that just says hello, this is like the response you should give. And then if you want to have more than one, you can have other cases here, or you can also compose these together where there are operators like plus plus or else. So this is actually a kind of a perfect example of how partial functions get used in ways that we kind of end up maybe using them every day, but we don't really think about them. And in fact, I mean, maybe that's a good suggestion. Maybe we should go back to our build file and let's see, do I have, yeah, I don't think I have ZIO HTTP as a dependency anywhere here. So maybe let me add that. That's going to be ZIO HTTP. And give me 1 second here. I'm just going to go and find the latest version of this. .0.0.RC2. Okay, so if I rebuild this. All right. Not reload. Thank you for nonsense. Files. Okay. So now that I have that, I can go back to here. And let me do some imports. I can see. All right. And so now if I do something, like let me see if I'm going to get the autocomplete. Yeah, so this is a perfect example here of, I think, unfortunately, of course, Metals is not actually working for me to let me click through here, which is good times. Maybe I'll see if I can get this to rebuild here. Where's my Metals thing? Let's try this. But if you click through this, what this HTTP collect function actually looks like is it's something that's taking a partial function. Let's say it's a partial function of request response here. And so what this partial function is saying, like what is a partial function? Why is a partial function different than another function? In kind of a good world, we would say we want functions to be total. And that means they should return an output for any input, right? So if we have something like def double it, and this takes an int, and it gives us back an int, and it's just going to multiply it by 2. This is, theoretically, this is defined for any int I can give it, right? I can give it a negative int, I can give it a positive int, I can give it 0, I can give it int.max value or min value, and whatever I do, it's always going to give me back an int. Maybe it's going to be a weird int if it overflows, but it's always going to give me back an int. So this is a function that is what we would call total. And generally, what we would say is that we want all of our functions to be total in this way, if we just define a function. So what we really don't want to do is to have something that's like double it 2 that says maybe if x is equal to 0, then exception, and then otherwise double it, right? This we would kind of say is bad. And maybe another way to think of this is not an honest type signature, right? Because we want someone to kind of not have to look at this at all. We want to be able to hide this. If maybe, yeah, perfect. If I kind of look at this, we want this type signature without me knowing anything else to tell me what this thing does. And what this thing says is, hey, you give me an int, I'm going to give you an int back. But we have to kind of click into it, and maybe we don't even, maybe it's hard for us to click into it. Maybe it's proprietary code, or it's going through 10 different other places, but we have to kind of go into it to see that like this isn't actually an honest type signature. And so one way that we can deal with that is we have something like, maybe we'll call it double it 3. I could make that more, say, honest, so to speak, by using some data type that represents failure here. And so now if I, instead of throwing an exception, I'm going to return this left side of an either here. And otherwise I'll return the int in the right-hand side. And so now if we, maybe I don't know if I can, there we go. Now if we look at this signature without knowing anything about the implementation, we know that this thing may not always give us back a int, but may give us back some string instead. And at this point, just from the signature, we don't really know what the string is supposed to represent or when this is going to occur, but we at least know that it may occur in some cases, and hopefully this method actually has some documentation that tells us when this is going to occur. So we could think of this as an example of turning a function that wasn't total into one that was total by explicitly representing the cases that aren't covered. I'm just going to check in for 1 sec on to see if anyone has any questions or comments. Nobody's joking at RC18. Yeah, sometimes we have a lot of RCs, but I don't think we're going to get anywhere close to RC18 here. And so this technique of making functions that weren't total be total by representing the error type can really use different ways of representing the error here. So another thing we can observe here is we need some way of representing the error, but we can use different ways of doing it. So this is one way here of we're like representing the error essentially as a string, and we're using either as our error type for this. Another way I could do it is I could also, like, doesn't have to be either, right? We could write the same thing, and maybe I'm going to use ZIO here. And we don't really need the power of ZIO here because there's nothing that's beyond having this failure. There's nothing that's asynchronous. There's nothing that's doing IO or side effects. Don't really need ZIO here, but we can use ZIO if we want to. And basically, we're doing the same thing here of we're modeling this failure possibility or this possibility of we don't want to handle this case in the error channel here. And we can also use a variety of error types here. So like these two in a way are both nice because they like provide some descriptive information about what the error was. But we could also say, well, maybe the string isn't ideal. Maybe we want to have some kind of sealed trait with case classes that represent specific types of errors that could occur. That could be like a nicer thing for us to do. We also don't necessarily have to have any information about the error. So let's go back and we'll see how many variations of doublet I can do. But let's do another one here where I'm going to go back to using the either. But this time, I'm going to use unit here. And so this I'll just make left unit. And this I'll just make right. And just start a compilation. Let's check myself here. And so this is at some level the same as all the other ones. It's saying that I don't handle this zero case. And I mean, if we're all really multiplying, maybe we don't need to worry about this, but in this case, we don't handle the zero case and we handle anything else. And you can think of the unit here as a failure with no additional information beyond I failed or I didn't match. So the downside of this is obviously we don't get any more descriptive message, but maybe we don't want to give a more descriptive message here. Maybe we just want to say like, look, there's a case of categories we don't cover, and this is how we're telling you this. And Kaninji is going exactly where I was going next, which is this either unit int type we can actually think as being equivalent to an option type. And so let me create one more of these. So these two actually contain exactly the same information, right? And we could think of this as we could say that basically a left of a unit is equal to none, and the right of an x is a sum. And we can see we could go back and forth between these and we'd never lose any information. We could always handle any case and we could always round trip back and forth between these. And if we use a library that gave us more abstractions like ZIO Prelude, we could even define an equivalence relationship that would precisely describe this. But in this case, I think this one is simple enough here that we can just kind of see from visual inspection that these are the same. And so this option is getting, or this function that returns an option is getting very close to what the partial function is in Scala. So we could say that a function from A to option B is itself equivalent to a partial function from A to B. Just like these two are two different ways of representing the same thing, these two are two different ways of representing the same thing. And we can actually go back and forth between them. So let's look a little bit more at what this partial function is. I think I can actually click through to this. And let me see, this might not be. So this partial function is basically defined in terms of these two different methods. So one is this is defined at, and then this other one is the apply method. And so we can actually see that of, let's say I want to create my own partial function. So I could say found my partial function. And this is going to be a partial function. We'll just kind of keep going with our little definition from int to int. And so there are a couple of ways I can define them. The first way is probably the way you'll never actually define it. But I'm going to do it here just to like be super explicit and kind of actually like show like what a partial function is. So a partial function, just like everything else in Scala, it's its own trait, right? I mean, we can see it's a trait here. So there's no magic to it. And to implement a trait, I just need to implement the abstract methods of the trait. And in the case of the partial function, there are these two different methods. And I'll just take these out for a sec so we can implement them. So there's one called isDefinedAt. And that basically says, hey, is this an input that this partial function wants to handle? And then the second one is, hey, handle this input. And so the contract of this is essentially that before you call apply, you're supposed to call isDefinedAt. So just like if you've ever worked with like an iterator, before you call next on the iterator, you need to check whether the iterator has next before you call apply on the partial function. You're supposed to check whether the function is actually defined at some input. And so here, if I wanted to be super explicit about my partial function here, I could say something like isDefinedAt as well, as long as it's not 0, I'm defined at that thing. And for the things I am defined at, just multiply them by 2. And we can actually use some of these operators that are built into Scala to prove out this equivalence between these two things. So if I have this thing called my partial function here, and I want to convert this, so let's call this val option function. And I want this to be just a function from an int to an option of int. I can use this lift operator. And it's maybe a little bit like arbitrary, like why you call it lift versus unlift, but that's what it's called here. So anytime I have a partial function, I can turn it into one of these functions that returns an option of whatever the result was here. And similarly, I could say val my partial function 2. And this is also going to be a partial function. Int. I could take my option function and I could unlift it. And once I'm done with this thing is going to be, for all practical purposes, the same as this thing. And maybe we can do a little bit of a test for ourselves here. Maybe we could say, my partial function to 2, and then print line, my partial function is defined at 0. And so we see when it applies, and here I was like cheating slightly if I should have really checked whether it was defined, and then I should have done this thing. But I'm just going to do it here. So I get 44, I double it, and then it says, hey, I'm not defined at 0. But if I did here, if I check whether it was defined at 2, that should give me true. So we can think of partial functions as just these functions that optionally return their values. And that's kind of another way of thinking about it. But the actual encoding of this partial function has these 2 different methods that basically say, are you defined at this thing? And then let you actually apply the function there. And the idea behind that is a little bit of an optimization of it. So just a little bit like when you work with the iterator interface, instead of wrapping every value you take out of the iterator with an option, you just check this, which returns a Boolean. So it can be a little bit more efficient that way. But so that's the idea of the partial function. So it's just a function that only handles some part of its input, or sometimes the domain of the function only handles some sets of inputs. And a lot of times this can be helpful when maybe it's hard with the type system to express the types of inputs that we take. So like in a way, the cleanest thing would be if we had some trait, or maybe I'll call it final case class non-zero int. If I had this and I could enforce this, then maybe it would be even cleaner here to have this not be a partial function, but just to have this be a function from a non-zero int to an int. But yeah, maybe it's not just, well, 0, maybe it's some other more arbitrary set of values that we don't handle. Maybe it's a little bit harder or just more awkward to represent it at the type level in terms of this input type. So this partial function can be pretty useful here. Any questions on that before we move on? I'm going to quickly just check on the Discord here. Okay. So the ways I've defined partial functions here, I would say like this is super explicit, but you're basically never going to actually, I think, see a partial function defined this way. I don't think I've ever seen someone define a partial function by actually implementing the trait themselves. And I would say even actually this, you can use this lift and unlift to go back and forth between them. But that's typically more like when you're like adapting something from one to the other that you already have versus like the basic way you'll construct these. And so the way you'll typically construct these in Scala is you'll construct them with this what I call like a partial function literal syntax. So let's do val my partial function, I think it was 3. And so this will also be a partial function. And what you'll just do is you'll have one of these oops. Yeah, I think I can actually take this out. Yeah. slightly. So I think this is probably the most typical way you would see these partial functions defined, is you just use a case statement yourself. And that lets you take advantage of a bunch of other nice features in Scala around pattern matching, where, I mean, here this was just an int, but maybe I want to define a person that has like a name and an age. And then if this person here, I can destructure this in the same statement here. So I could do person, name, age, if age is greater than 18, say, and then maybe give me back their name, right? So then, and now this maybe has some like extract name if not minor or something. And so this gets to, I think, one of the really nice things about these partial functions in Scala is we can define them with this partial function literal syntax, and we can take advantage of all the nice things about pattern matching here, right? So I can destructure this, and I could destructure this like all the levels I wanted to. So like, let's say I made this more strongly typed, and I had like a name that has a value that's a string, and an age, so I don't want to mix up my different integers and strings. And so I could dig into this if I wanted to, and I could do like that. And I can kind of get as fancy. Oh. And I can get as fancy as I want to here. And we can see that this is now starting to get a little bit closer to this like way we were defining these routes, right? Where it's like a little bit less obvious here because this is kind of using some like fancy syntax here, but this is just another pattern like this one up here. And so in both cases, we can see some of the like nice things about this of we're able to have constants that we're matching on. So like here, we're saying, well, only match if this is a get, only match if the first thing after it is hello. And similarly, I could do the same thing here. So maybe I only want to extract the name out if this person's name is Adam. So I can both kind of match on values and require them to satisfy certain constraints. And I can also bind these variables here. So like in addition to maybe here, I'm kind of adding a condition on the age, or if I wanted to, I could say, maybe I only want to do this if someone is, I don't know why, 17. So I can both match on some variables, and I can extract some variables and I can do something with them. I can return them, or I can print them, or I can do anything else with them. And this is all kind of just built in vanilla Scala. So we can kind of see how I think that was a pretty intuitive and attractive way to define these routes, right? It kind of takes advantage of the syntax that we already know. We get to both like basically require certain things, right? Require that this route starts with hello. And then we also get to extract these variables. Like we say, like, okay, the thing after the slash, after the hello, we're going to call that the name, and whatever it is, we're going to respond back and say hello to that name. So that's kind of the good of partial functions. And a lot of times, like here, we end up using them and we may not even realize it here. Like, let me, ooh, it looks like I can actually click through this. And so, yeah, here you see this perfect example that this thing, when you do that HTTP.collect, that's actually taking a partial function. But you probably didn't even realize that it was a partial function. You just did the pattern matching thing. because just like we can use this function literal syntax, if I've got a function literal like this, if the type can be inferred, I don't even need the rest of this. And so that's what you're basically seeing happen here. This is a partial function literal, just like this is here. So that's kind of the good. I'm just briefly check in on chat here. So let's talk a little bit about maybe what is less than ideal about this. And to do that, I'm going to make something explicit, which has been, we call implicit here, which is when are we actually doing this testing? So let's create some new examples down here. So let's say def my partial function. I don't know if I'm 3 or 4. Maybe I'm at 4. And this will be, say, a partial function from string to string. And we use the same literal. But this time, I'm going to create a new function that I'm going to call matches. And yeah, I'll just say, welcome to Zymposium. And what I'm going to do with this matches thing is I'm going to just find this as my own function. And it's just going to take 2 values that are both strings. And it's just going to return back a Boolean. And it's going to tell me whether they're equal. But I'm going to throw in one more thing here, which is I'm going to throw in a print line statement that says check, say like debug, checking if left matches. Compiles. Okay. So I've got my partial function here. And let's try using this. So maybe I'll actually use that lift thing we looked at before. So I'll lift this. So now this is going to be a function that takes a string and gives me back an option here. And then I'm going to feed it hello. And let me just take away my other print lines just so we don't confuse ourselves. And let's try running this. Okay, so we see that we had to, obviously before we did this thing, we had to at least once run this thing and check if hello matched hello. And then maybe let me also just print this out so we get the final result of this. So we see we had to check whether the input matched what we were expecting for this, we'll call this kind of a poor man's route. And so we checked once, it did, and then we returned the result that we were supposed to for this little poor man's route that we created. And there's actually a little bit of optimization that Scala is doing under the hood here to make sure that we only check this once, that we don't kind of check it once when we check if the partial function is defined this thing, and then again when we apply it. But that's kind of a little bit of an under the hood thing that Scala does. So, okay, that's fine. Let's now look at what happens when we essentially add more routes here. And we'll look at 2 ways I can do kind of more routes. So one way I can do a route, and maybe I'll call this my route. And now I'm going to define, I'll call this maybe my route 1, or maybe this will be, yeah, let's even be more careful. Let's call this hello route. And then why don't we have another one that's called goodbye route. And so this will be a partial function, also string to string. And yeah, if they say goodbye, we'll say, see you later. That seems like a very friendly introduction. And so partial functions can actually compose together. So let's call this val my routes is equal to hello route or else goodbye route. Take this away for a sec, just look at this. Let's make sure this compiles. And let's spend a second here on what this or else thing is doing. So we can think of combining these routes by saying, well, first try to match this route. And if this route matches, then great, giving back its result. And if not, try this other route. And if this route matches, then great, do whatever it says. And if not, then eventually say, hey, none of these things matched. And if we go back to our like option function, we could even make this like more explicit. So let's try to do it just with these optional functions just to kind of see what this looks like. So we could say like def or else. And so we're going to have one thing that's, maybe I'll call this, be a little bit polymorphic here, call this A or B. And so we'll have one function from A to option to B. And then we'll have another function from A to option B. And so let's just do it kind of explicitly here. So I've got an A to start with. So we could say, okay, call left of A and match on it. And you're either going to get a B, in which case you just return that, or you're going to get a none, and then you are going to return the right. And we could use more like higher level operators if we wanted to, but I think it's kind of nice to just do the, and in fact, to do the pattern matching here just to be like very explicit about what's going on here. So let's now take this set of routes that I've created and let's see what happens when I try a couple of different inputs for it. So first thing I'm going to do is I'm going to call it with my first route here. And so this does the same thing we saw before. It checks the first route, and if the first route matches, it returns the result. And it's just done there because the first route did match. So now though, let's try the goodbye. So now, we start to see something interesting, which is that when we compose these routes together, we have to check each of the routes linearly to find the one that matches, or eventually we have to check them all and see that none of them match. And that kind of comes right out of this or else operator, or this one we implemented ourselves here, where basically the way this is always going to work is we're just going to take each of these routes and we're going to try to match it. And if it does, we're going to go on and do that thing. And otherwise, we're going to go on to the next one. And in this case, I only had 2, so it wasn't that many, but probably like a bunch of you here, if you've like actually like implemented APIs with one of these HV libraries, you probably don't just have 2 routes. You probably have 20 routes or you have 50 routes. And this is just going to keep adding up here, right? So let's just add a couple of others. Some other route. And let's see. Something else. I don't know. And yet another route. And so we can put all these together, right? Which at this level looks very nice. So we can put all these routes together. But now let's say that my route ends up being farther down here. So look what we did. We checked every one of these routes. And this probably is not the end of the world, right? Hopefully the time that we're spending sending things across the network is more than the time we're spending just parsing these things. But the point of having a library is we want to make things as efficient as it can be. And so essentially doing this lookup, having this lookup be ON is not very good when, right, if we kind of think about this more fundamentally and we say like, basically what I have is kind of, at least in the simple case where I'm not binding variables, like this whole thing is basically a map from like string to string. And we know if I have a map, I can do way better, right? If the map is sorted, I can do it in log time. If the map is a hash map, I should be able to do it in constant time. So my kind of algorithmic performance here is actually pretty terrible to the extent that I care about that. Let me just check in and then I'll kind of show one other thing here. And so some of these like, okay, let's not be so mean to the partial function. I'm not trying to be mean to it at all. I mean, I think part of the point of these is like different tools are good for different things and use them where they make sense. So like a very common use of a partial function would be, let's see, if I have like my ZIO is equal to like ZIO dot fail boom, let's say. So I could do my ZIO, and then I could do this catch sum. So this catch sum is another operator that maybe didn't realize it under the hood uses a partial function and basically says like, hey, I want to catch some of my errors and I don't want to catch the other ones. And you can use the nice pattern matching for that. So that's all well and good. And you're probably not going to compose 20 different partial functions together to do your little error handler here. So that's probably totally fine. So I don't think it's like partial functions are like bad at all, but just like kind of use the tool for the right case and recognize where maybe we've kind of overused a tool here. So anyway, so one issue we saw here is this performance one, right? That when we're kind of matching on these little routes we have here, that we have ON time and we should be able to have way better time. The other issue we have here is that we have really poor error reporting. And that really goes back to this idea of the partial function being isomorphic to, and sorry for the big word, but basically equivalent to this function that returns an option. And really early on, we said that the option was representing failure, but not having any information about why a failure occurred. So like if I go back down here and let's say I do something that doesn't match at all. Let's say I do, let's say I'm trying to do hello, but I actually make a mistake of, for some reason, I think the API is like, you should capitalize it. Or maybe I think it's case insensitive, or I just do that. So let's try running this. And so look at what we got here. So we checked all of these different routes. That was the first problem we saw before. But the other problem is now we're getting just none as our error type here. So I kind of like, okay, the route didn't match, fair enough. But I've got no information to like help me about like, what did I do wrong here? Maybe there's something that was like really close to this, right? Wouldn't it be nice if instead of none, this returns something that was basically equivalent to like a left, no routes matched. The closest route was hello. Did you mean that? right? That would be like a way nicer message to get than none here. But it's impossible for the partial functions to do that because they're essentially these functions that just return options. Or if we go to the low-level representation of the partial function, all they do is they just say, am I defined at this thing or not? They don't say, why am I not defined? They just say, I'm not defined. So it's impossible with this encoding to have more descriptive messages than just the route didn't match here. So all of this is leading up to this idea that, and I'd really encourage you, John did a tweet about this and he did the PR about this. So take a look at that on ZIO HTTP if you're interested in it. This is kind of just, I guess, kind of building the foundation for that. But essentially, we can do way better here if instead of using these partial functions, we actually have values, right? It's the same thing we describe a lot of times when we're like working with ZIO of we want things to be first-class values so we can really work with them and compose them. And so when we have a description of a workflow, we want that to be a ZIO and that to be a value that we can compose with other things and not just to be some kind of thunk or something. And when we have something that's running computation, we want it to be a fiber so we can interrupt it or we can join it or we can check what's going on with it. So we want all these things to be values. And when we kind of start to think about it, this partial function is really making the kind of left-hand side of this not a value, right? This whole thing is just obscured by this one partial function. We don't get to really look at, or in a way that's more sophisticated than just or else them together, compose this. So you can imagine instead, we have something like we have some kind of, let's call it like a sealed trait, that maybe we call it like a pattern. And so the pattern would represent the left-hand side of this. And maybe this right-hand side, maybe I'm just going to call right now, maybe I'm going to have a handler. And maybe this is going to be some kind of ZIO here. And if I had those, then we could imagine maybe at that point a route is a combination of a pattern and a handler. And then I could have a set of routes that's just a chunk of these routes. And so to like put this here, let's try to, again, we're definitely not going to do like the whole implementation in ZIO HTTP, but let's like do a really simple one. So yeah, so one type of this would be a literal, right? We'd probably have a literal, we'd have some kind of variable, we'd have some kind of and then that represents we have these different things. But right now, let's just try to like mirror this thing here. We have these like 4 things. And so each of these could be represented as a literal. And in this really simple case where they're all literals, when we compile this and we go to match on this, that we could just compile this down to a hash map. In other cases, we can't do a hash map because we may have these different variables in here, but we could do a much more efficient hierarchical matching, right? Where if you imagine, like, let's go to some of our roots here. Where did I have this? So like here, let's create like a couple of maybe more realistic things. So let's say this is going to be like user, and then maybe we'll have like add, and then here we'll have like user delete. And what we'll see for these is they have this hierarchical structure, right? Where like we're going to have a bunch of ones that are going to be under user, and we have another bunch that are going to be under, account or whatever domain object we're working with here. And so we can be way more efficient than just linearly going through these by essentially grouping them into a tree where we have all the user ones together, we have all the account ones together. And so the first thing we do is we look at it and we see whether it starts with user or whether it starts with account, and then we just dive into that subtree here. And so by doing that, you can go from n to essentially log n performance here. So you get both better performance, as well as, again, we can have like much better error messages here, because what this is going to end up being is just a data structure that we can introspect on. And we could say like, okay, if you gave me some particular inputs and I had this set of routes, we can look at the routes and we can have some algorithm that's going to say, what is the closest route to that? And maybe we can say, did you mean that route? If we think that's within some distance, and right, we could use like unassigned distance, or we could do other stuff for that. So that's kind of the idea here. And that's what's coming to ZIO HTTP with some of the changes that John is working on. So I'd encourage everyone to check out that PR. And I think it's really interesting. I think it's a nice like example of, we had this thing and it kind of fit, right? It was very easy. It was very nice to do it this way, but we're essentially going to do it in a very similar way. So let's see, let me find my little HTTP example. So basically, you're not going to have this case statement, but the way you might do it now is you might say like val route 1 is that, and val route 2, oops, sorry, my mouse is going crazy here. Where'd it go? Is that, and then you say val my routes is equal to routes route 1, route 2. That's a little bit of pseudocode here, but that's what you're going to end up doing. So it's going to look very, very similar to what you had before. But it's now going to have this greater introspectability and greater performance and better error reporting. Yeah, I think it's a kind of cool example of rethinking something that seems pretty basic, but actually has some practical implications. All right, let me check in on questions here. Yeah, so Pavel says, right, we can use a tree, similar to a prefix tree, for matching on the strings. And yeah, that's exactly right. I mean, if we have this super simple case where they're all literally strings, we may be better off just hashing them all and just like taking the one that matches exactly. But that's right. In the real situation, we're going to have kind of more complicated situations where we have like, I mean, if we go back to like our example here, we've got like a literal, and then we have a variable, and then, or sorry, we have a literal and then a variable, and then we may have another literal and then another variable after that. So yeah, a tree or prefix tree, something like that, or radix tree, it can be a very efficient solution for that. So yeah, that's exactly right. Let me check in on the Discord as well. Okay, great. And someone took a look at the PR. So Naveed said, can we take a look at the PR together? Yeah, I think we briefly can at least. Give me 1 sec to just share, do a different screen share here. So yeah, so someone sent the link to it. So it's this routes one that John has been working on. And you can see he did a very nice description, but this is the same idea. You have this route pattern here. So this is how you would describe like, hey, this pattern is looking for a get. It's looking for the thing after it to be users. Sorry, let me maybe make it bigger. So it's not make it big. Yep. It's looking for users, then it's looking for an int, and it's going to have this labeled user ID. It's looking for post, and then it's looking for a string after that. And so, I mean, I think this is a giant PR because it's just like trying to refactor a ton of things. But let me see if I can find. Yeah, so this is kind of getting at some of those core data structures here. And part of the idea of this was to, and yeah, there's this routing tree for that kind of optimized implementation. And part of the idea of this was also to unify the endpoints API with the more, with kind of the more classic ZIO HTTP API, because there was already the endpoints API that was very declarative and did encode all these things as values because it needed to have codecs for all of them. But then at the lower level, we had just this like partial function. So it's really trying to unify those things. There's definitely still stuff that's work in process here, which is why I kind of wanted to, at least for this Zymposium, focus on more like the concept of it. So like everyone like had the like foundation for like what this is and like why it's cool versus like all the particulars, because I think there are things that like still figuring out. But yeah, definitely like check that out. As you can see, there's like lots of stuff here, and there's a nice description there. John also did a nice tweet about some of the thinking behind this. And he actually talked about, he did another not ZIO HTTP, he did another HTTP library called Blue Eyes a long, long time ago that was kind of the precursor of all HTTP libraries in Scala, that actually did like start the pattern of using a partial function. So yeah, it's one of those things that we all have to kind of clean up our original sins at some point. But yeah, definitely would encourage everyone to check that out. Let me just check in one more time on the chat here. And then Juan asks, is the structure created at compile time or at runtime? So it'd be created at runtime, but the idea is it would be created once when you create your server. So you like create this map when you create the server, and then hopefully the server is handling thousands or tens or hundreds of thousands of requests. And each time you're doing that, you're just using this optimized tree that was constructed the one time at the beginning of your application you created your server. Okay, I see Naveed is typing, so I'll give him maybe one more minute, and then I haven't done the benchmark yet. I know this is still in the process of getting optimized. It's definitely it's definitely one of those things where I'm sure that like the biggest thing is just going to be your transport or going back and forth, but you also want to make the server as efficient as possible. But yeah, so I think that's what I got here. Maybe I'll give one more minute. I see a couple of people typing, so I'll give folks a minute here. So RF Maya. So I think it's so much the JVM optimize it as we can optimize it. So I mean, I think that gets to one of those things of like when you do that pattern match, like it's easy to think that like it's not linear, but in general is linear. The main exception to that is if it can be compiled to a switch statement, then it can be more efficient. But that basically means that like each of them has to be just like a number, which isn't the case with having these when we want to be like buying these variables and do these more sophisticated things than just there are these 18 cases and we want to pick which of them applies. So that lets us do that optimization. All right, cool. Well, thanks everyone for joining, especially on a summer afternoon or evening. Hope everyone has a fantastic weekend, and especially for those of us who are in the US, it's 4th of July weekend. So I hope everyone enjoys the weekend and maybe has Monday off if people are fortunate. And yeah, we'll be back with more stuff. I think we got a couple of other fun libraries we're going to be talking about, and lots of good stuff to come. So hope everyone has a great weekend. Bye.